डॉक्टर अखिलेश शिक्षक आप लाइव हैं।
Thank you, sir. Very good evening to all. I am Dr. Akil Ahmed Sheikh. Today's topic is here linear algebra. In this topic, the subtopics includes are inverse of a matrix, rank of a matrix, consistency, eigenvalues, eigenvectors, and use of Cayley-Hamilton theorem. First of all, just I introduce the some basic definitions of matrices, which will be useful. Here, you know that here upper triangular matrix, that is a square matrix whose lower diagonal, or we can say that lower of diagonal elements are zero, is called upper triangular matrix. Then singular matrix here, if determinant of A equals to zero, that is singular. That is determinant A equals to zero. Then non-singular matrix, if determinant of A is not equals to zero. This plays an important role when we find the inverse of the matrix. When the matrix is, or we can say that when the determinant is non-singular, then its inverse is exist. Now, there are some properties, a formula to find inverse of matrix. A inverse is equals to 1 upon determinant of A into adjoint of A. Here A is just any square matrix, and condition is that the matrix A is non-singular. We can see that determinant of A is not equals to 0. Then there is one important topic which is here eigenvalues and eigenvectors. In this case, and eigenvectors. Most of the examples has been asked on eigenvalues and eigenvector. Here, the roots of the equation, that is determinant of A minus lambda I equals to 0. This equation is also called as characteristic equation. Then the roots of the equation determinant of A minus lambda I equal to 0 is called eigenvalues of the matrix capital A. Next is here the set of eigenvalues. It means that if the given matrix is of order 3 by 3, then the given matrix has 3 eigenvalues. If the matrix having order 2 by 2, it has 2 eigenvalues. So all eigenvalues combinedly, or we can say that the set of eigenvalues of capital A is here matrix, is called the spectrum of capital A. This is the important sentence, that is spectrum of capital A. Spectrum is nothing but the set of eigenvalues or all eigenvalues of the matrix capital A. Then next is here how to find eigenvector. We consider a minus lambda I into x equals to 0. Here A is any square matrix, lambda is here eigen value, or it is a scalar. I is here identity matrix, x is here column matrix. This equation is used to find the corresponding eigenvector. This equation is used to find the corresponding eigenvector. Corresponding means if lambda 1 is the eigenvalue, then for value lambda 1 we find the value of x1, that is corresponding eigenvector. When second eigenvalue is lambda 2, then we find x2, that is second corresponding eigenvector. Then there are some results depending on eigenvalues and eigenvectors. Eigenvalues of matrix capital A is equals to the eigenvalues of the matrix A transpose. Means eigenvalues of matrix A and its transpose both are same. Next here, sum of eigenvalues this is the important note. Sum of eigenvalues equals to trace of the matrix capital A. What is trace? Trace is nothing but the sum of the diagonal elements. Sum of the diagonal elements of capital A, matrix capital A. Next important note is here. First for sum of eigenvalues. Next for product of eigenvalues. Product of eigenvalues is nothing but the determinant of the given matrix capital A. Next note here. In a and diagonal matrix, triangular means it may be a upper triangular matrix or it may be a lower triangular matrix, and diagonal matrix, the eigenvalues are nothing but the diagonal elements themselves. Means if you have given diagonal matrix, then its diagonal elements is nothing but the eigenvalues. Now here, how to find eigenvalues? Now for 2 by 2 matrix. Is formula here, lambda square minus s1 lambda plus determinant of a equals to 0. Second here, for 2 by 2 matrix, what is s1? I just express after this second point is lambda cube minus s1 lambda square plus s2 lambda minus determinant of a equals to 0. Just noted that here sign are alternating starting with positive sign. Here S1 stands for sum of diagonal element of A. S2 is here. This is the sum of minors of diagonal elements of capital A. Then by using this result we can find the eigenvalues. And by using A minus lambda I into capital X equals to 0, we can find corresponding eigenvector. Now here there is one statement, or you can say the theorem, that is called as here Cayley-Hamilton theorem. Cayley-Hamilton theorem. It said that every square matrix satisfies its own characteristic equation. Its own characteristic equation. And what is characteristic equation? The polynomial determinant of a minus lambda I equal to 0 is called as characteristic equation. These are some basic definitions which will be required for solving the values related to matrices. Now here we discuss some example here. First example, the trace and determinant of a 2 by 2 matrix are known to be -2 and -35 respectively. Then its eigenvalues are Options are here: minus 30 and minus 5. Option B are here: minus 35 and minus 1. Option C: minus 7 and 5. Option D is here: 17.5 and minus 2. Then we have given trace and determinant of a matrix of a 2 by 2 matrix are minus 2 and minus 35. Then what is trace? Trace is nothing but the sum of eigenvalues. Sum of eigenvalues. We have given matrix of order 2 by 2. Obviously, there will be two eigenvalues. So we assume lambda 1 and lambda 2 are two eigenvalues. So we are given trace as minus 2 and eigenvalues are here lambda 1 plus lambda 2. Next, given condition is here: determinant is given and we know that here the relationship between determinant and eigenvalues is here the product of eigenvalues is nothing but the determinant of the matrix. So which is here minus 35. We just take here lambda 1 into lambda 2. Now just check the option. Which option satisfy this condition? That is, sum is minus 2, means sum of two eigenvalues is minus 2, and product of these two eigenvalues is minus 35. First option is here. First option, sum is here minus 30 plus minus 5 is minus 35. Not satisfying first option. Then second option minus 36. Again not satisfied is again second option. Check third option, minus 7 plus 5 is minus 2. Is satisfy first condition. Second here, 7 5s are 35 into minus 1 means minus 35. Again satisfy second option. So obviously option C is the correct answer. Now next example. The matrix has eigenvalues minus 1 and minus 2 and the corresponding eigenvectors are 1 minus 1 and 1 minus 2. Respectively. Then the given matrix is then the matrix is we have given here four options. Option A is here 1 1 minus 1 2. Option B is here 1 2 minus 2 minus 4. Option C is here minus 1 0 0 minus 2, and option D is here 0 1 minus 2, minus 3. First of all, what is given? The matrix has eigenvalues minus 1 and minus 2, and we have given eigenvectors, and we have to find the corresponding matrix. So first of all, we form a model matrix because we know that here the result from diagonal matrix, that is B inverse AB equals to D, that is diagonal matrix. What is B? Here B is nothing but the model matrix. Here A is the given matrix. This matrix B is here model matrix. This D is here diagonal matrix, and we know that very well that this diagonal matrix contain its diagonal elements nothing but the eigenvalues, or in other words we can say that eigenvalues are nothing but the diagonal elements of the given matrix capital D. So from given matrix, from eigenvectors we form model matrix B. Eigenvector is here 1 minus 1 and 1 minus 2, and diagonal matrix D is here we form from eigenvalues. Eigenvalues is here minus 1 and minus 2, which will be diagonal elements. Now from equation above, that is B inverse AB, we can write here as B inverse AB equals to capital D. But here we are interested to find the value of capital A. So first of all we have to remove this B inverse. So pre-multiplying by capital B on both sides, what happened? This B inverse A into B equals to BD. Next, B inverse becomes I identity. Identity matrix into any matrix becomes a same matrix. It remains here AB equals to BD. Here matrices does not follow the cancellation law which satisfied in algebraic. Next, again here we have to remove this B. So pre-multiplying by B inverse, we get here A B into B inverse equals to B D B inverse. So this B inverse becomes I identity. It remains A equals to B D B inverse. Now the multiplication of these three matrices is nothing but the given matrix of matrix A. Now here in examination you can use scientific calci. You can multiply these three matrices and you will get the matrix A. So here we multiplying these three matrices manually. First of all, we have to find B inverse. So B inverse is nothing but 1 upon determinant of B into adjoint of B. What is B? B matrix is given, that is 1 1 minus 1, minus 2. Then its adjoint here. To find adjoint, we just interchanging these principal diagonal elements, which becomes minus 2 and 1, and multiplying by minus 1 to remaining element, which becomes 1, and this is minus 1. This is the adjoint of B. Now to find determinant of B, it is here minus 2 into 1, minus 2, minus of minus 1, minus minus plus, it becomes minus 1. So B inverse equals to minus 1, which is the value of determinant of B, and adjoint of B is here minus 2, minus 1, 1, and 1. Then multiplying by minus 1, it becomes multiplying each element of the matrix by minus 1, it becomes 2, 1, minus 1, minus 1. Now, substituting these values in capital A is here B, D, B inverse. So matrix B is here 1, 1, minus 1, minus 2. Matrix D is here minus 1, 0, 0, minus 2. And matrix B inverse is here 2, 1, minus 1, minus 1. Now you can multiply these three matrices at a time by using calci, or by using manually. We can multiplying first these two matrices using elementary row transformation. So row by column, 1 into minus 1 is minus 1, plus 1 into 0 is 0, it is minus 1. Next, row by column, 1 into 0, 0, plus 1 into minus 2 is minus 2. Second row by column, minus 1 into minus 1 is plus 1, into plus 0, this becomes 1. Row by column, minus 1 into 0, 0, plus minus 2 into minus 2 becomes plus 4. Second matrix here, 2, 1, minus 1 as it is, and minus 1. Then again multiplying these two matrices by using row by column method. Row by column, minus 2, minus 1 is plus 2, becomes 0. Row by column, minus 1, plus 2, minus 1 plus 2 is here 1. Row by column, 2 ones are 2, minus 4, 2 minus 4 is minus 2. And next limit is here, row by column, 1 minus 4 is minus 3. So in given example, option D is the correct option. Option D is the correct option. Next example. The product of eigenvalues of the matrix capital P is, what is P? P is here 2, 0, 1, 4, minus 3, 3, 0, 2, minus 1. And options are here minus 6, 2, 6, and minus 2. Now here, this is the matrix P, that is 2, 0, 1, 4, minus 3, 3, 0, 2, minus 1. Now here, we have to find the product of the eigenvalues of the matrix P. But we know that the product of eigenvalues is nothing but the determinant of the matrix. So we find determinant of P, and directly we will get the product of eigenvalues. Instead of finding eigenvalues by using lambda cube minus s1 lambda square plus s2 lambda minus determinant of A, we just find its determinant. So first 2 into, just ignoring first row, first column, and finding the determinant of these remaining elements. It becomes here minus 3 into minus 1 becomes plus 3 minus 3 to the 6 minus 0 into any term becomes 0 and signal alternating. Next term is here plus 1 into, ignoring first row and third column, taking determinant of remaining elements. So 4 to the 8 minus 0 means it is 8. So it becomes here 2 into 3 minus 6, it is minus 3 plus 8. It is here 3 to the minus 6 plus 8. We will get here 2. So 2, nothing but option B is the correct option. Now, next example. The determinant of a 2 by 2 matrix is 50 if one eigenvalue of the matrix is 10, then the other eigenvalue is then option is not given. We have to find the answer. Question is given. The determinant of a 2 by 2 matrix is 50, and we know that there is a relationship between eigenvalues and determinant of a matrix. That is, determinant of a matrix is nothing but product of eigenvalues. And determinant is given, which is 50. The matrix is here 2 by 2. So assume there are two eigenvalues, that is lambda 1 into lambda 2. And we have given that there is a one eigenvalue which is 10. So just assume here one of the eigenvalue, that is lambda 1 equals to 10. So substitute this value in this equation. We get here 50 equals to 10 into lambda 2. We get here lambda 2 equals to 5. So the another eigenvalue is nothing but 5. We satisfy this given condition. Now, next example is here. The condition for which the eigenvalues of the matrix capital A equals to 2, 1, 1k are positive is, options are given, k is greater than 1 by 2. Option B is here, k should be greater than minus 2. Option C, k greater than 0. Option D, k less than minus 1 by 2. Means for which value of k the eigenvalues will be positive. Now here, we know that here determinant of A is nothing but the product of eigenvalues. Means both eigenvalues may be a negative or both eigenvalues is positive. The condition is that here what is condition? The condition for the eigenvalues is here determinant of A is greater than 0. When determinant of A is greater than 0, then its eigenvalues are positive. So matrix is here 2 1 1k. So it's 2 1 1k. This is the determinant should be greater than 0. So determinant is here twice k minus 1, twice k minus 1 greater than 0. So it is twice k greater than 1. So k greater than 1 by 2. So k greater than 1 by 2. This is the condition for positive eigenvalues. Now, next example. Given that the determinant of the matrix one 3 0 2 6 4 minus 1 0 2 is minus 12, then the determinant of the matrix is given 2, 6, 0, 4, 12, 8, minus 2, 0, 4 is, we have to find the determinant of this matrix. So this is the, we just consider this matrix in terms of determinant, which is here 2, 6, 0, 4, 12, 8, minus 2, 0, 4. Now there is the property of determinant when we take any element column, any element common, either from row or from column, then there is only change in that specific row or column. So from first row, we just take 2 as a common, then remaining limit is here 2, 1, 3, 0. Then from second row, we can take 4 as a common, but check here given determinant, which is here 130. Second row is here 264. So when we take 4 as common, it becomes 1. So from second row, we take 2 as common again. So it remains 2, 2 6 are 12, 2 4 are 8. From third row again, we take 2 common, because we have given third row as minus 1 0 2. It becomes minus 1 0 2. Then check here, the value of determinant is given, and multiplication of this term, that is 2 into 2 into 2, is 8, and the value of this determinant is given, which is here minus 12. So 12 8s are 96, minus n as it is. So minus 96 is the answer. Next example. This type of example most of the times asked. The matrix 1 2 4 3 0 6 1 1 e. This is the 3 by 3 matrix. Has one eigenvalue equal to 3. Then the sum of the other two eigenvalues is, no, option is given p, p minus 1, p minus 2, p minus 3. This question can be asked in another way. Instead of p, there may be any value, and option will be changed also. Then what is question is given? The given matrix has one eigenvalue which is equal to 3, and here we have to find the sum of the remaining eigenvalues. So we know that here the relationship between eigenvalues and the trace of the matrix. The sum of eigenvalues is nothing but the trace of the matrix A. What is trace of A? We already mentioned in note. Trace of A is nothing but the sum of diagonal elements of capital A. So, in the given matrix, 1, 0, P are the diagonal elements. So, the given matrix is about order 3 by 3. To assume here lambda 1, lambda 2, lambda 3 as a eigenvalues. So, sum of eigenvalues is equals to trace of A. Trace of A nothing but sum of diagonal element of capital A, which is given here 1 plus 0 plus P. It is here 1 plus P. Again, we have given one of the eigenvalue is 3. So just let us assume any one eigenvalue as a given eigenvalue, which is 3. Just put here value. It becomes 3 plus lambda 2 plus lambda 3 equals to 1 plus P. So lambda 2 plus lambda 3 equals to 1 plus P minus 3. So here we have to find the sum of remaining two eigenvalues, which will be here minus 2 plus P or P minus 2. So in the given option, option C is the correct option. Option C is the here correct option. Next, let here A, B, C, D be n by n matrices, that is square matrices of order n, each with non-zero determinant, and if A, B, C, D equals to identity matrix I, then B inverse is option A, ACD, option B, CDA, option C, DCA, option D, ADC. Now just check the question here. A, B, C, D are having n matrix, that is square matrix, each matrix with non-zero determinant, that is inverse of each matrices exists. So we have to find B inverse. We have given here, since A, B, C, D equals to I, that is identity matrix. So taking inverse on both sides, what happens? It becomes A, B, C, D 4 raised to minus 1 equals to I inverse. Now this is the property of matrix. Here we cannot apply laws of indices as it is. In laws of indices, it becomes A inverse, B inverse, C inverse into D inverse. But in matrices, matrix multiplication is not commutative. That is, AB is not always equals to BA. In matrices, we start from D, right side. That is, it becomes D inverse, C inverse, B inverse, A inverse equals to I inverse. And I inverse equals to again I, because inverse of any identity matrix is again same matrix. Now we are pre-multiplying by D inverse. Here just pre-multiplying by D inverse. Then what happen here? This D into D inverse becomes identity matrix. So it remains here. I just write here again term D inverse, C inverse, B inverse, A inverse equals to I. Then here we are interested to find the value of B inverse. Here we have to make D inverse, C inverse, I inverse as a identity matrix. So D into D inverse is 1, the identity matrix. So pre-multiplying by D, we get here D into D inverse, C inverse, B inverse, A inverse equals to D into I, again D. His D inverse becomes identity matrix. It remains here C inverse, B inverse, A inverse equals to D. Now we have to remove here C inverse. So pre-multiplying by C on both sides. So C inverse, this is B inverse, A inverse equals to C into D. C inverse becomes I, identity matrix. So I into any term becomes same element. It remains here B inverse into A inverse equals to CD. Now here we have to find the value of B inverse. For that purpose, we have to reduce A inverse in terms of identity matrix. So post multiplying by A, it becomes B inverse A inverse into A equals to CDA. Here pre and post multiplication is important in matrices. Then A inverse into A becomes identity matrix. It remains here only B inverse, which is equal to CDA. This is the final answer. And CDA is nothing but option B is the correct option. In terms of matrices, we have to remember that matrix multiplication is not always commutative. Now, next example is here. The determinant of matrix A capital A is 5 and the determinant of matrix B is 40, then the determinant of matrix AB is. Now, let us just solve this example here. Here, we are given that determinant of matrix A is here 5 and determinant of matrix B is here 40. Now here we have to find the determinant of A, B. So we know that here determinant of AB is nothing but determinant of A into determinant of B. It is here 5 into 40. So it is here 200. So 200 is the answer. Example. Given an orthogonal matrix, matrix is here 1 1 1 1 is 4 by 4 matrix 1 1 minus 1 minus 1 1 minus 1 0 0 0 0 1 minus 1. Then A into A transpose inverse is. So in this case we have to find A into N transpose its inverse. If you find A transpose multiplication of these two matrices, it becomes tedious. It is not possible because it is the 4 by 4 matrix. Let's check the given condition. We are given that the given matrix is an orthogonal since A is an orthogonal matrix. So we know that here if A is orthogonal, so A into A transpose equals to I. Now taking inverse on both sides, we get A transpose inverse equals to I inverse. Again, we know that inverse of identity matrix, again the same matrix, that is I. So I is the final answer. Next example here. For the given matrix, matrix A is given 2 minus 2 3 minus 2 minus 1 6 1 2 0. One of the eigenvalues is 3, then the other two eigenvalues are, options are given 2 minus 5, option B is given 3 minus 5, option C is given 2 5, option D is given 3 5. This is the same example as discussed previously, which is in terms of P. Last element, that is element of last entry, is P. Now here we are using the same concept. Here we know that sum of eigenvalues is equals to the trace of the matrix or sum of the diagonal elements of capital A. The sum of eigenvalues equals to trace of matrix capital A. The given matrices of order 3 by 3, we just assume three eigenvalues lambda 1, lambda 2, lambda 3. So trace of matrix A, that is sum of diagonal elements of A, that is here 2 minus 1 plus 0. This 2 minus 1 0. These are the principal diagonal elements, which is here 2 minus 1 plus 0, which is equals to 1. Now we have given one eigenvalue as 3. So just let here lambda 1 equals to 3, the given eigenvalue. So what happened? Just substitute the values in our equation. We get here 3 plus lambda 2 plus lambda 3 equals to 1. So lambda 2 plus lambda 3 is here. Lambda 2 plus lambda 3 equals to becomes 1 minus 3, which is here minus 2. Then just check the options here. Sum of eigenvalues must be minus 2. Check the option. Then first option is here 2 plus 2 minus 5 is minus 3. No. 3 minus 5, we get here minus 2. This is the correct option. Other options are not possible. So this is the answer. So these are some examples on eigenvalues, eigenvector, which has been asked in previous GATE examinations. So I stop here. Thank you. Thank you, friends.
Thank you so much, sir.
Neeraj sir, over to you.
Thank you so much. Today was your last day of mathematics class. 10 classes over. Thank you so much.